Good morning, class. So today we're going to carry on with determining what the doping level is depending upon the Fermi level. And to start doing that, we have to understand the density of states. And we went over last time that for a empty box where u equals 0 outside and u equals infinity inside, that g of e, the density of states, is equal to m to the 3/2, the square root of 2 times energy over pi squared h bar to the 3rd. And the way to understand that is that the way I want to explain that is that for the empty box, it's like energy starts at 0 and versus kr goes up quadratically. And so when you calculate the density of states, and remember the picture of the sphere in the spherical shell, it goes up as the square root of e. Meaning the density of states is 0 at the bottom of the band, and then it goes up with the square root of energy. And the way to see that is that in K space, as you increase energy, you increase the size of the sphere. And the K volume goes as 4 pi kr squared dkr, meaning the K volume is 0 when the sphere is small, and it goes up as the radius goes up. And so basically the number of states for that sphere and for that sphere in the shell go up as the square root of e. And we went over last time how you calculate that. But you can kind of see it pictorially. As the sphere gets bigger, the number of states in that shell gets bigger, and when you do the math, you find out that it goes as the square root of e. Okay, now that's for an empty box. Now we have to do a real semiconductor with bands. Now, the simple answer is very easy. And the simple answer is that, and I'm going to draw this and I'm going to erase it then so we can look at it more formally. But the simple answer is just that, okay, this is drawing what kind of what a band looks like if you have an empty box. Now when you do actual band structure, all right, well, all it is that the conduction band starts at some energy, E sub c. And so, you know, this is for an empty box. For this situation, I mean, the simplest way to think about it is we just replace E with E minus EC. Now besides that, okay, for the empty box, m is the mass of an electron, of a free electron. Whereas what I've taught you is that when you do band structure, you find that the curvature of this band is not the same as the curvature that would be given by a free electron. And so, again, it's very simple. You just replace M with M star. So it's pretty easy to think about, really. And, you know, I don't want you to get hung up on thinking about it any other way. There's really no reason to. But part of the reason why I gave you the homework problem of the two-dimensional crystal is because, and I'm just going to erase this for a second here so that we can think about a two-dimensional crystal. For a two-dimensional crystal, you can actually draw multiple bands, if you think about it. Because now, okay, I can draw a coordinate system that's kx and ky. And I can retain the third coordinate that us three-dimensional creatures can think about for energy. And so for a 2D crystal, you can talk about or draw an actual band structure, and it would look like a bowl in this coordinate system I'm drawing. And the valence band would look like an inverted bowl. And so you can think about calculating G of E at a certain E minus EC by doing the analysis that you're doing in your homework. And we'll go over that in the next lecture because I don't want to give away the homework answer. But all I'm trying to do here is illustrate to you that going from an empty box to an actual band structure, it's not really mysterious. It's just that because for a three-dimensional crystal, we can't retain a fourth axis for energy. We can't draw this picture that we can for a 2D crystal. For a 2D crystal, you can think about it very simply. Okay, this is what the band structure actually looks like when we retain the 2 dimensions in K space, and it just looks like this bowl. And so you can think about, you know, that the density of states starts at this point and then goes up from there. So however you need to think about it, all we have to do is modify that and that. And then we have the density of states as E increases above E sub C for the conduction band. All right, so that's pretty easy. Now, as we said, and I'll put it right here so we have just have a place for it. N at a certain energy, right, is, I'll write G first, the density of states at that energy times the probability of being occupied at that energy. So let me draw a real band structure with the conduction band. E versus K. Here's the valence band. And let's draw F of E. Now, what I've told you is that the Fermi energy is going to be somewhere in the band gap. And again, the way you have to think about it is that if you put in more donors, meaning make it more n-type, EF has to go up, okay, because it has to obey Fermi direct statistics. If you put in more acceptors, EF goes down. And so basically, it's like EF is our barometer of what we've done to the crystal in terms of how much doping of what type we've put in. And so EF can move around in there, and we draw F. All right, remember it's 1 when the energy is well below EF. Okay, here's EF. I'll mark E sub C. And remember what F is. Now remember, whenever you write EF, or write F, the way to think about it is that it goes down with energy. And so because this is in the denominator, the E comes first, because then it gets smaller with E. And so it's always 1/2 at EF, and it basically does something like that. Now, in order to come up with the sort of simplest answer for n, because we're going to have to perform the integral of this, we want to simplify f, and we can do that as long as this energy is much greater than kT. All right, so basically we're going to do approximate that EC minus EF is much bigger than kT. Now, if we do that, I mean, you can sort of see mathematically first. All right, if F is 1 plus E to the E minus EF over kT. All right. Now this means, remember, we're only interested in energies higher than the conduction band energy. So this means that for E greater than EC, this is approximately, okay, this term is much bigger than 1 then, right? See, if I put in E sub C there, E sub C minus EF, if that's much bigger than kT, that's e to a big number. So that's much bigger than 1. So I can write that as 1 over E, approximately 1 over E to the E minus EF over kT, which is equal to E, now I'm just going to put a minus sign, negative E minus EF over kT. Now the other way to think about it is that you can sort of draw it pictorially, and I really should get colored chalk, but basically if this is the real F, the approximate F, sorry, I'm just going to point toward it, right, looks like this. Right, because for this, if E equals EF, that would be 1. And so there, the approximation is valid. And since we're only interested in energies above the bottom of the conduction band, we're good to go. Now, I just want to do a disclaimer now at this point, because for the rest of the course, we're going to be assuming that this is true. Now, when we do P, we're also going to be assuming that EF is not closer than KT to the valence band either, because when we calculate P, we're going to do the same thing in reverse. So for this course, we're confining EF to that range, where this is, something like, okay, maybe like 3 KT. Now, so what that means is that we're confining our analysis to doping levels, whether they're donor or acceptor, that keep EF in that range. Now, how do we calculate? Okay, so first of all, what does that mean? Okay, it basically means that as long as you don't dope the semiconductor really, really heavily, we're okay with this analysis. Now, an advanced course in solid-state physics would circle back at some point and calculate N or P if it got within that range. Maybe we'll do that when we finish up with the main material of the course. Okay, so that's the disclaimer. We're only calculating for that doping range. Now, you may be wondering, okay, well, what actual doping range is that? Well, we're going to calculate basically N and P in terms of where EF is here, and if we want to know what doping level that corresponds to, then we go back and we do our charge neutrality analysis, and we figure out what that is. So, it's all self-connected. Right now, we're only concerned with calculating what N is. Okay, so let's continue here, and what I'm going to do is I'm going to erase this and start doing the math. So we got G of E for our conduction band, and we're going to write that F of E is approximately equal to E to the minus E minus EF over KT, which is valid above above the bottom of the conduction band, as long as EF doesn't get too close. Okay, now you may kind of be getting annoyed because I'm putting a minus in, and it's because I want you to think about F here correctly, since we're talking about energies above the conduction band bottom. All right, and EF is in the band gap, obviously. E minus EF is a positive quantity for this analysis. So I want to impress upon you, then that's E to the minus some positive quantity, and so that's the correct way to think about it. Okay, if I flipped it and put positive signs, it would actually get more confusing. So for energies above the conduction band minimum, this is a positive quantity, so this is E to the minus a positive quantity, which is of course less than 1. All right, so now we just integrate. So N of E is equal to the integral of F of E, G of E, now, where do we integrate? Well, we integrate from the bottom of the conduction band to infinity. So plugging in, and we have to put our approximate sign here because we're using an approximate value for F. So there's F. And then for G, what I'm going to write is, I'm just going to write G as A times EC, or sorry, E minus EC to the 1/2. So I don't have to rewrite all those M stars and H bar and everything. So I'm just going to put A times EC, I'm sorry, E minus EC to the 1/2 dE. So that's N. I'm sorry, this should not have been N as a function of E. That is N. The way to think about it, if you know, you're sort of mathematically a purist, this is N of E, or the volume density of electrons at each energy. And so when I integrate them, I get the total value N. Okay, so now we just have to do this integral. And, you know, what you're going to see is you just do a few substitutions. It's pretty simple, really. And the sort of the quickest way to get to it. So first, what we're going to do is we're gonna write this integral. And now I am going to break up the exponent. Okay, so now I did break up the exponent so you can see each part. So e to the minus e over kt, e to the ef over kt. And now I'm going to do something that looks, you know, weird at first, but you'll see it allows us to put things together. I'm going to write here EC over KT and e to the minus EC over KT, and then the rest of it here. So what I've done is, you know, it looks like kind of a waste of time. I put in an e to the EC over KT and an e to the minus. Of course, when you multiply them together, you get 1, and you know, e to the 0 is 1. And so it looks at first like I haven't done anything, but the reason why I've done that is because, you know, next what I'm going to do, let me bring that A out of here. Now I'm going to bring this out. Okay, so I brought out that one, right, because that doesn't depend on energy. I can bring it out of the integral. And I'm going to bring this one out. Okay, and that leaves inside that one. And that leaves inside that one. And you can probably jump ahead and see what I'm getting at here. Which is that now I can write this as, and I'm going to collect these terms with the minus sign outside. And I didn't leave myself enough room. Let me put that down a little bit. So you see I collected these two terms, and I collected them in such a way that, remember, because EC is bigger than EF, so this is e to the minus a positive quantity. And now I'm going to write this the same way. Okay, and those of you, you know, somewhat mathematically tuned in here, see that the reason why I did that is because now I have a common argument. or variable. Okay, I'm going to erase this part now, and you know, basically all you have to remember is we've used this approximation for f, which means that we're confined to, you know, we can't get closer than a few kT to either band. Okay, so continuing with the integral, n is equal to a okay, so that's that term in our integral. Okay, now I guess I should have done the change in variable first, but let me just do it here and then I'll write up there. I'm going to define x as e minus ec over kt. And then dx is just dE over kt. So dE is equal to kt dx, and also e minus ec is equal to ktx. Now, so now I'm going to write my integral in terms of x. Now at e equals ec, x equals 0, still goes to infinity. And now this becomes e to the minus x. And then this one becomes kt to the 1/2 times x to the 1/2 dx. Oh, sorry. Times kt dx. Sorry. You'll remember this sort of thing from your freshman calculus classes, right? When you do integrals and they have lots of stuff in them, you always try to write it down as some sort of simpler version of itself. And so basically what happens is that those kts come out. Because there's a kt to 1/2 and a kt, times the integral from 0 to infinity of e to the minus x, x to the 1/2 dx. All right, let's go back for a little bit and just, you know, kind of look here first. Remember, we're integrating above e sub c. So what you see is that f goes down exponentially as I go up in energy. The density of states goes up as a square root, and so, you know, this if I well, let me just do it this way. E to the minus x, x to the 1/2. Okay, it starts out at 0, right? Because that's x is 0 there, and it starts going up, kind of as the square root, but then it goes down again because I have the exponent in it, and so the integral of it is something you can figure out. You know, basically, you look it up. It's one of those table of integrals thing, and it's equal to, and you know, I always have to look at it. Remember, square root of pi over 2. You know, meaning because we've rendered it and there's this dimensionless, sort of meaningless variable x, it has a finite, you know, when you integrate the whole thing, it has a finite value that's independent of everything else you're doing. So n is equal to a kt to the 3/2 times the square root of pi over 2. And now if we plug in A there, so that's m star to 3/2 square root of 2 pi squared h bar to the third. I'll put that there. That's our integral. And kt to the 3/2. Oops. Okay, I left out the most important part here. I forgot to include my e to the minus EC over. Okay, so let me, what I do, this is the factor. Let me put the EC. Again, I apologize. When I went from this step to that step, I forgot to include that, which is kind of the most important thing here. So n, now let me collect terms here. I'm going to sort of do it in somewhat real time here. You can see basically there's a lot of 3/2 going on here. There's of course an m star to the 3/2, there's a kt to the 3/2, there's an h squared to the 3/2. There's a pi to the 3/2 because 2 minus 1/2 is 3/2. And so when you put everything together, it's 1 over root 2, because that's that. And then what people usually do is they put m star kt over pi h bar squared to the 3/2. And that's the answer. So basically, what it shows is that it goes as this sort of prefactor independent of the Fermi energy times this exponential, which depends upon the Fermi energy in that manner. And so what you can see here is that as the Fermi energy gets closer to E sub c, remember it can't get too close, that this positive quantity becomes smaller and e to the minus a smaller quantity gets bigger. And that's usually defined as something called n sub c, capital N sub c, e to the minus ec minus ef over kt, where nc is defined as this stuff here. Now, a good exercise, maybe it's a good homework problem, is to show that this thing has the units of 1 over volume, right? And we call this the effective density of states, meaning it's an effective value of density determined by m star, temperature, and such. Now let's look at this for a second, and what I'm going to do is I'm going to erase this. Okay. Now let's draw our band structure. And let's put in EF. here. And so what we found is that n is equal to n sub c, this quantity here, e to the minus ec minus ef over kt, where this is e sub c. So basically, if I draw E sub f, now I've been putting the zero of the top of the I've been putting the top of the valence band at equal 0. Okay, let's just continue doing that. Remember, I could put it anywhere I want. I could have put the 0 down here somewhere and called that E sub v, which I did in the notes. But let's keep going with this picture. So if this is E sub c, right, what this is showing is that n goes up exponentially as EF gets closer to E sub c. Because it goes as e to the minus EF minus EC. Now remember, okay, that must remain much bigger than KT. So this answer is only valid up to within a few KT of the conduction band. Now, what about P? Okay, P is the same thing. Okay, it's the integral, and now what I'm going to do is I'm going to integrate this way. So I'm going to go from 0 to minus infinity of G for the valence band of E F of, and now here, because the existence of a hole is the absence of an electron, I have to write 1 minus F of E dE. Now, what I want you to do is think about inverting this. All right, so that is 1 minus 1 over 1 plus e to the e minus ef over kt. All right. Now, if I do that, right, that's 1 plus, I'll just put e there, minus 1 over 1 plus e, you know, where I'm not writing out the whole thing. And I'll do that so you know them. That's what I'm doing here. And that cancels, and that's e to the squiggle over 1 plus e to the squiggle. And so when I write that out, I can write that out as 1 over 1 plus e to the minus squiggle. Okay, meaning the point is that I've essentially inverted the problem. Now we could spend, you know, another half an hour doing P, all right, and you know, if we did it, right, we would basically invert all the energy stuff. And so now we would invert that, so that would become 0 to infinity. G of E would still be, I erased it, G of E would still be M star, and now that's to the valence band. Okay, I'm doing G first. All right, let me do F first. F of E would still be e to the minus. Now, think about it. Okay, because I'm going down now, and I'm going to e to the minus, it's the same thing in reverse. And so now this becomes e to the minus, again, e minus ef over kt, because I'm integrating going negative in e. So it's the same thing, basically. You're doing the same analysis, just in reverse. And then I put G, and it's, you know, again my A, but I got to mark down A for the valence band, times E and 1/2 because I put the 0 at E equals 0. And so it's the same interval again. All right. It could be useful to go through that with all the inversions correctly and everything, but I'm just going to write down the answer because you can sort of see by the symmetry that it's going to be the same answer just with one thing flipped. Now, I'm going to have to specify here C, because that's M star for the conduction band, and that for the valence band. Now, okay, think about it. What am I going to put here? Okay, I still want to do my convention. Remember, when I did this, I wrote EC minus EF because that's a positive quantity. All right, I want to do the same thing here, but now think about it. Now, you know, let's say EF moves down to there. Okay, I'm making it p-type. All right. I want this to be my positive quantity because that is my positive quantity. And now, okay, I'm gonna call that E sub V, meaning the top of the valence band, just so we have some symmetry here. Now, think about it. What's the positive quantity? The positive quantity is now EF minus EV. So now, you know, and I drew things with EV equals 0, but you get the point here. Now, P, so this would be N, P would go up exponentially as EF gets closer to the valence band. You get it? So it's pretty neat, really, and I can complete my analysis here by defining this thing as N sub V. Okay, EF minus EV over KT. And what you see is that NC and NV are the same thing except with the different effective masses. If the effective masses of the valence and the conduction band were the same, they would be equal to each other. And again, I've written things so that it's e to the minus a positive quantity. For the case of electrons, that positive quantity is EC minus EF. For the case of holes, it's EF minus EV. Because EF ranges between EV and EC. And so for electrons, the positive quantity is EC minus EF, and it's e to the minus that over KT. For holes, it's EF minus EV, and it goes up as it gets closer to the valence band. All right, so let's just sit there and one more time go over this, okay, because this is our answer here. This is what N and P are. Using the Fermi energy as our sort of parameter, telling us what N and P are. That as the Fermi energy varies in the band gap, depending on our doping level. Now, how do we know where Fermi energy is? Well, we're going to do that next time. You know, how do we know, based upon the doping level, what the Fermi energy is? We'll go over that next time. But as EF varies, you know, if I dope N type, it goes that way. If I dope P type, it goes that way. N is N sub C, this stuff, times e to the minus the positive quantity EC minus EF over KT. And P is this stuff, N sub V, times e to the minus EF minus EV, which is that positive quantity. Okay? Good? All right. So the good news is the answer became very simple. N is this, and P is this. Now, all right, now we finally get to what I said I was going to prove, that before the midterm, I said just remember that this is true and we'll prove it later. So now we're proving it. N times P is equal to NC NV e to the minus EC minus EF over KT e to the minus EF minus EV over KT, right? I just multiply them together. Now look at it. That EF is a positive. That EF is a negative. They cancel out. Independent. You know, one thing as a professor you find out is that for some reason, when you're writing on the blackboard, you lose the ability to spell. I think it's because you're seeing the word too close. Anyway, independent of EF, right? It doesn't matter what EF is. See, as EF goes this way, P goes up, N goes down. As EF goes that way, P goes down, N goes up. So their product is a constant. And so, since it's independent of EF, it's independent of doping. Meaning it doesn't matter how many acceptors or donors I put in or what quantity, the product of NP is a constant. Okay, and let me go over here. All right, because this is our answer here. So NP is a constant. For zero doping, right? For zero doping, okay, because remember our charge neutrality, right? N plus, okay, now what's on this side? Remember, it's the acceptor, because when the acceptor becomes ionized, it becomes negatively charged. And a donor becomes positively charged. Remember, that's our charge neutrality. For zero doping, Na and Nd are zero, so N equals P. And we define that as N sub I, the intrinsic carrier density. So here, right, NP is that. So this is equal to Ni squared. Ni squared is Nc Nv. Now, what is that? That's Ec minus Ev. That's the gap. So, what is Ni? Ni is the square root of that. Or Nc to the 1/2 Nv to the 1/2 e to the negative E gap over 2 kT. So what have we done? We've determined what N and P are. They're these things. All right. Where we define Nc as this, and we define Nv as this. And we show that the product is independent of Fermi energy, so independent of doping. And since it's zero doping, N times P is Ni squared. And so let me go over that again. At zero doping, N equals P equals Ni. So let me put this off to the side here. At zero doping, N equals P equals Ni squared. So at zero doping, continuing on, N times P is Ni. So at zero doping, Np is equal to Ni squared. Zero doping, by definition. But Np is a constant. We showed that. So Np is always equal to Ni squared. Okay, maybe that's too convoluted of an explanation, but because N equals P is equal to Ni at zero doping, Np is Ni squared at zero doping. And because Np is a constant, Np is always equal to what it was at zero doping, Ni squared. And so Ni is the square root of this product we determined from our band structure analysis. So Ni is equal to that. Now, let me put in part of Nc and Nv, the temperature part. So I'm going to put in, I'll call it B. Okay, the temperature part of Nc and Nv is this here, so it's T to the third, right? All right, so these two factors kind of compete with each other a little bit. This goes up with temperature. This goes. This also goes up with temperature. If you think about it, I'm sorry, they don't compete with each other, because when T equals 0, this is E equal to minus infinity. So this is equal to 0 at T equals 0. And of course that makes perfect sense, because at T equals 0, there's no thermal energy to get an electron from the valence band to the conduction band. So everything fits together, right? Ni is this thing. It's independent of, it doesn't depend on doping or anything like that, but it does depend on temperature. So Ni goes up when the temperature goes up, and the product of Np is always equal to Ni squared. And what we've done in this lecture is, okay, this this was super important rule that I made you memorize before the midterm, even though I didn't explain how it was true, because it's so important to remember that. And now I've both proved it and also shown what N and P actually are as you change the doping and move EF along in the band gap. So that's the end of this lecture. This lecture has shown what N and P are. Their product is Ni is constant, independent of EF, and what Ni actually is. The other thing to see here is that Ni goes down as the band gap goes up, because then this is e to the minus a bigger thing. And again, that makes perfect sense, because if the band gap gets larger, it takes more thermal energy to get an electron from the valence band to the conduction band. Okay, very, very good. So that ends this lecture. Thank you.